Now, in this lecture, what we will do, we will see another paradigm of designing algorithms, which is called the greedy strategy. As the name suggests, again we will be seeing some of the optimized version of the problems, some optimal problems, where we want to optimize some criteria. Now, the strategy says we will see something very locally. So we will decide on the future by seeing what is best locally, what is good locally, and we will choose that best one locally, and we will not bother about the what will happen in the for the entire global one. If that strategy works, that calls the greedy algorithm. Sometimes we will see even this local evaluation works for the global optimization. Suppose we want to optimize some criteria globally, even if seeing it locally helps. In that case, we will be using these greedy algorithms. The best thing about the greedy algorithms are that the algorithm is most of the time very simple, very intuitive, because anybody would do that way. But the hardest part of this algorithm is to prove that it will really give you the optimal solution. So let's start with a very trivial example. Suppose we have this problem. You will give me the solution almost immediately. Choose a subset of a set S of objects AI such that sigma AI belongs to T. T is the subset. Wi is less than equal to W, where W has been given, and this T is maximized. So W is the input. So you have been given a set of objects AI, where each one with weight Wi. Wi is the weight of the object AI. So you want to choose a subset T from the set S such that if you sum the weights, it should be less than the given weight W. And what do you have to optimize? The optimize criteria, the criteria for optimization is this, the number of elements in T. That should be maximized. Yes, that's the immediate solution. So this is a trivial example. That's the immediate solution. You take the least weights and just go on summing until unless the total weight becomes more than W. Okay. So this is just to illustrate what is the greedy strategy. This is a very greedy strategy, that I know that if I take the next one which is the best, it will in this case it will solve the problem. So if I write the algorithm, what will be the algorithm? Sort so that Wi is less than Wj if I is less than j. You have to sort that way. So basically it means you just sort all the Wi's, all the weights, and index them such that when Wi is less than Wj, then I will be less than j. Once we have done that, then we just do start with empty set T. Initially W of T is equal to 0, I is equal to 1, while Wt plus Wi is less than equal to W, do T is equal to T union AI, and Wt is W of T plus Wi. I is equal to, this is a very straightforward algorithm. I don't have to explain what it is. So basically you have sorted them, then taking one by one into your bin and checking the total weight is less than W or not. and take as many as possible. So this you know that it will solve your problem. This will maximize the total number of elements you have taken. Why it is greedy? Because here you are taking the next best one. Because you have sorted them, you are taking the next best one. But in this case, it happens that this greedy strategy also gives you the global optimum. That it will maximize this number of elements. Okay. Just to tell you this I just to tell you what does it mean, the greedy strategy. I'll take a little bit non-trivial example. So this is the next problem which is called the scheduling problem. So what is the scheduling problem? We have a set S in of activities, some activity, and each activity I has a starting point Si and a finishing point Fi. So Si is the starting time and Fi is the finishing time. Each activity has these two times. So now we have to run all these activities on some resource. So that the condition is that resource cannot have two activities together. So it's like a process running on a it's a single CPU which can only one process can run on a single CPU. Right? At any point of time only one process can run. So suppose these are the processes and it has a starting time and finishing time and CPU is the resource. Okay. So this is the condition. So what is the optimal version of this problem? We have to maximize the number of activities scheduled. To maximize the number of scheduled activities. Okay, so this is the criteria to be maximized. So you schedule them such that the total number it may not be possible to schedule everybody, because their starting and finishing time may be so much overlapping that you would not be able to schedule all of them. But in that case, then maximize the total number of activities you can schedule. So in this case, the solution is not that straightforward like the previous problem. How would you solve this problem? How do you solve this problem? The solution is not that straightforward. It's not so difficult also, but it's not very trivial. But again, we'll see this greedy strategy works quite well in this case. Has anybody some idea? How would you do this?
Starting time and finishing time.
Starting time and finishing. Suppose, like say one job in a computer. It has a time interval. Between this interval, you can run it. You cannot run beyond this interval. You cannot run before this interval. This is just an abstract problem.
It is not a find the starting time.
Definitely, it is the time it takes. Because the finishing time minus the starting time will be the total time it is taking. But your starting time cannot be before than that. That's a constraint. And once you start it, it will take up at least that much time to finish it. Fi minus Si. Not at least, exactly that much time. Okay, so any idea how to solve this problem?
First of all, find all the finishing times which are matching with the
right. Somebody told me.
Suppose take the one which takes less time.
No, that is not the use.
So the least SI.
So which finishes as earliest?
Right. So you take the activities which finishes the earliest. So that should be your strategy. First take the job which finishes the earliest. Then take the rest of the jobs which do not intersect with this job. How do you represent this job? So let's see. So suppose I have this time interval. So let's take this. So suppose these are the jobs. So you look at the finishing time. Look at the finishing times. So earliest one is this one. So you choose this. And then delete all of the other ones which are intersecting, because once you run it, these two you cannot run. You have chosen this, so you delete this two. You take the next one, which is this. So you take this. Again you delete, in this case nothing to delete. So you choose this. Then the next one, which you choose this, in that case you cannot take this. So these three will be an optimal solution. Actually in this case there is more than one optimal solution, it may be. Maybe there are other three activities which can also be scheduled. But the total number cannot be more than 3 in this case. Okay. So once we have agreed that this works, but one needs to prove it, why it works. One needs to prove that if I take the earliest one, which finishes the earliest, if I take this greedy strategy, that will work, you need to prove it also gives you the global optimum. I'll come to the proof later. Let me first write down the algorithm then. So what should be the algorithm? Sort so that fi is less than fj if I is less than j. So you basically again sort with respect to the finishing times. To t is equal to 1, last is equal to 1 for, this is a very simple for loop, for 2 to n do if f last is less than equal to si, then t is equal to t union I, last is equal to I end if end for. So you have first sorted with respect to the finishing times, then you took the first one, that is the one, this one will give you the one which finishes the first. So that is the one you have put, that is 1, t is equal to 1. Then from I2 to n do if f last, here you are just checking whether it is those ones which are intersecting with the chosen one, you just delete them, otherwise you take them. Otherwise here it is, you are taking t is equal to t union I, and you update your last is equal to I. Okay, it goes on in this flow. Now this simple strategy, how much time does it take? No, it's not order. You missed one part. There is a sorting. Order of n log n. So step 1 will be much more than step 2. So it is order n log n. Okay. So this step 2 is order n, but step 1 is n log n. So that's why this entire thing is n log n. Now let me argue why this works. Why this entire strategy works. Okay. The argument is quite nice. So how do we prove? So claim is this. The presented algorithm, the presented greedy algorithm schedules the largest number of activities. It schedules the largest number of activities. That's what our optimal problem was, to schedule the highest number of jobs. So how do you prove? First you observe this. Suppose there is an optimal choice of these jobs, some choice of this job. So I just draw this one choice, maybe this. Like suppose this is an optimal choice. I just drew it. There is one. Now I can claim that the first job according to our algorithm, that is the one which has the least finishing time, can always be chosen. Can always be chosen to replace one of the jobs from here. The job which has the least finishing time, it must be less than this. Either this one is the first one which has been chosen, we are done. Otherwise, it must be somewhere here. I can always replace this person and replace it with this, the first one. This is the one. And still it remains an optimal one, right? Because there were total number of 4, that was the largest number, still it is total number of 4. So I replace the first one in your optimal solution with the first job in my sorted order. And that cannot hamper the optimal size. Now you can carry on this argument. Once you have taken the one, the next one chosen by the algorithm will be the next finishing time. But this entire argument can be carried through. Now on the rest of the jobs, again I take the next one, this must be less than this, can go on. So every time this argument is replacing one job from the optimal one which you have chosen with the one which the algorithm is choosing. What does that mean? It means the algorithm must have computed one optimal solution. Have you seen the logic here? Okay. So let's see. So what I am doing, you just take one optimal solution. Can you follow this? That there is one optimal solution, I have just taken that optimal solution. Now my claim is the first job in that optimal solution can always be replaced by the first job the algorithm chooses. Can you follow why it is so? Because the algorithm chooses the first one is the one with the least finishing time. So this finishing time must be less than this finishing time. So it must be to the left of it. So if I choose this does not hamper any of this one. So if I choose, I replace this one with this one, then also it remains an optimal solution. Right? If you have believed this argument, you just carry forward this argument over the rest of the jobs. Now you replace this next one with the one which the algorithm has chosen. Its finishing time must be less than this guy again. So you can choose that one again. So this is the optimal one, and this is the algorithm choose, which it is choosing. So I am replacing one by one with the algorithm choice. So which means that the algorithm, whatever it is choosing, it must be another optimal solution. Because your choice of the optimal solution, I have replaced each one of them with another job chosen by the algorithm. So that is why it is working.
So can't we go with the other way around, taking the maximum SI and then go backward?
Take the maximum of SI.
SI.
Probably it will work. You need to see. Yes. You need to see whether this argument can be worked. But I guess yes. Probably you are right. Because it's very symmetric. You can carry forward this entire argument from the backward direction. So then in that case it will be the maximum. Yes, I think it works. You just carry this argument from this direction, from the rightward direction. Then it will be the maximum of SI, which will work, I think. Okay, but you cannot take the minimum of SI. I think that does not work. Okay, so this is what is called one greedy algorithm. We will see later part of our course actually some graph algorithm where I can tell you particularly where this greedy algorithm is working really nicely. That will be a perfect example where this paradigm works quite nicely for that particular problem. It's called the shortest path problem on graphs. So it's called the Dijkstra's shortest path algorithm, where actually this entire greedy strategy is working very nicely. But there the proof is also a little bit more cumbersome. So that is the paradigm for the greedy algorithm. So sometimes, suppose you cannot do anything, the first thing probably you should try whether the greedy strategy is working for the problem. Something to be optimized, first try the greedy strategy. Whatever is the best locally, choose that one. It may not work. In that case, probably you have to look to the dynamic programming paradigm. Whether the dynamic programming paradigm works. It may be so that the dynamic programming also does not work in a straightforward manner. It might have to be changed. It may be so that even that one does not work. Then probably you should design your own you should come up with your own innovations. Or maybe that problem is not solvable in polynomial. In that case, you should not try designing polynomial time algorithms. So let me stop on greedy strategy algorithm, because as I told you, the later part of the course I will come to another problem on graphs where I will explain this one more. Let me move to another topic which is called the amortized analysis. I will just introduce this subject so that you become familiar with this strategy. Now this time I am shifting from algorithm to analysis. So far we have seen different paradigms of algorithm design, and we have also analyzed the algorithm quite straightforward manner. Actually, analysis was not that difficult, except at one place where you remember we were analyzing the complexity of heap construction. There we really did something a little bit novel in analyzing that the construction of heap was linear, not n log n. Okay, so here is another strategy which will tell you where the analysis could be made much better. A straightforward analysis may not give you something which is better. So this is another strategy or another paradigm or analysis, not on the design. So to illustrate this, let me take one example, one problem, which is called the binary counting. So what is the binary counting? Binary counting uses an array A. So I am just taking 6 positions, 2, 1, 0. So A has 6 positions, 0 to 5, A0 to A5. Each one has either a 1 or a 0, and the value of the number given 1s and 0 is nothing but whatever it represents in binary. So suppose I have say 0, 0, 0, 0, 0. So this basically n is equal to 0. The next one will be 0, 0, 0, 0, 0, 1, which is 2. Sorry, 1. Then 0, 0, 0, 0, 1, 0, 2. 0, 0, 0, 0, 1, 1, which is 3. Then 0, 0, 0, 0, 1, 0, 0, which is 4. It goes on. Okay. So the problem is this. So the array A starts with all zeros, then it has to increment this value of the number by 1. The value initially is 0, then it will increment to 1, then it will increment to 2, then it will increment to 3, then it will increment to 4. So in algorithm, how do you do it? This is the algorithm. So we are going to increment the value of the number represented by the array A in binary. So procedure increment I is equal to 0, while if you look at this one, what should be the algorithm actually? When we basically we are going from left to right, as long as I see 1, nothing is done. Basically all ones should be converted to 0, and first 0 should be converted to 1. That's what it is happening here. So first 0, this is converted to 1 here. When you go from 1 to 2, 1 I convert it to 0, Then the first 0 converted to 1, stop. Okay, so like here, now this is the first 0, 1. Now this is interesting. Now here, 1 converted, first 0, 1, stop. So that's the algorithm. That's the algorithm does. So I'm going to write this while AI is equal to 1, do AI is equal to 0, I is equal to I plus 1, end while. And when you have converted all ones to 0, then come to AI, which you make it as 1. So this is the algorithm. This is the binary counter. You are incrementing this binary representation such that it goes incrementing the value by 1. 0, 1, 2, 3, 4. Now the question is, this is the question. What is the total time or number of steps if we increment starting at 0 all the way up to n minus 1. So suppose we are incrementing the value from 0 to n minus 1. Then what is the total number of steps needed? Can somebody tell me what is it? N into n minus. So he is saying it is n into n minus 1 over 2. Does everybody agree? Why are you saying it is n into n minus 1 over 2? Because in the worst case it can go up to, so the complexity will be 1, 2, 3, 4 up to n. What is your logic?
So for each number, like the number of elements you go in the array, that will be good.
No, this is not true. First of all, tell me, if you are going to increment from 0 to n, what should be the length of the array?
So it's summation of log I from 0 to n.
Log I from 0 to, so basically no, if you have to represent a number of value n, how many bits do you require? Log n. One, precisely it is, you require 1 plus something like log n. Sorry, see, this is a float. 1 plus log n bits are required, or positions. Positions in A are required for n. Okay, so and each single increment, how much, in the worst case, how much time does it take? In the worst case, each increment takes how much? This while loop will go over how many bits? N cannot be there. Yeah, all log of n. It can go up to all the bits. So log n. So how many steps, how many incrementation are there? N. So n incrementing, and each one is taking order of log n. So how much total time? N log n. So it's better than n into n minus 1 over 2. So it is definitely order of n log n. This is the analysis you are doing. But again, here lies the question. Is it better? Actually, it is better than n log n or not? And the answer is yes. Answer is actually the total time is n, not order n log n. It is better than that, which is order n. It is linear. So how can we analyze it? So here is a method to analyze it using the amortized analysis. What is the amortized analysis? What does it mean? It means, see, when we analyze this one to be n log n, we saw each step individually, each incrementation step individually, and we took the worst case for each incrementation. But that is not like in the heap analysis. should not have taken the worst case for each step there. Here also, if we see into a global picture, probably it is much better. So we will see into the global picture so that the analysis becomes better. And that is why it is called the amortized analysis. What do we mean by amortize here? Suppose some incrementing step is taking too much of time, it will be amortized over some other incrementing step which is taking much less time. Because your interest is not on a single step. Your interest is on the total over the entire incrementing from 0 to n. So some step may be taking too much, say log n, but some step may be taking only 1 or 2. So why don't we amortize, or why don't we spread the cost of the log n steps over this 1 or 2, so that on an average the total steps behavior becomes much better. So essentially what I am saying, suppose one step is a log n, another step is 2, another step is another 2-3 steps are 2, you can take out this log n steps and distribute this cost over those steps which are less, and you can claim on an average probably each step is say constant. If you do this, then you can claim that n step will take order in time. That is precisely which is the principle of amortized analysis. Okay, we will see this analysis later in some other data structure called Fibonacci heap, which I will be taking next after this topic, where you will see how this amortized analysis will be really useful. Now let us see how do you do the amortized analysis here. Here is one strategy. There may be more than one strategy. I am just telling you one strategy here. So define, the strategy is very nice actually. Define the amortized cost changing 0 to 1 as rupees 2. We are associating with each change some rupees, some cost. Okay. So whenever we are changing from 0 to 1, we are attaching 2 rupees to it. Okay, 0 to 1. Now when changing 1 to 0, it has a cost of rupees 0. You remember, if you go back to the algorithm, what we are doing? We are seeing all the ones, making ones to zeros, then the first 0 we are making 0 to 1. So you are changing 1 to 0 and 1 0 to 1. Right? So changing from 0 to 1, it has a cost of 2 rupees. Okay? Just assume it for the time being. I will tell you the logic why you do that. From 0 to 1, it has 2 rupees cost, and from 1 to 0, it does not have any cost. Does not cost us anything, suppose. Okay, with this assumption, which you don't want to believe, because there is a cost, I am still saying it is 0, but it will be paid. It will be paid. That cost will be paid. So with this assumption, each increment has how much cost? Each increment has how much amortized cost? Tell me that. Only rupees 2. Each increment has amortized cost rupees 2 only. So total cost is what? If this is the total amortized cost is what? For entire n increment step? 2n. So suppose if I can show that with this cost, if I can cover everything, with this much of money, if I can cover all the 1 to 0 and 0 to 1 change, I'll be done. This much money I have paid, total 2n money I have paid, but I did not cover this step 1 to 0. I did not tell you explicitly. But if I tell you that this much money is enough even to cover that one, will be satisfied, right? So now I am arguing on that. When you are going from 0 to 1, I have a cost basically. When 0 to 1, I have paid 2 rupees. But this 2 rupees, 1 rupee will go to it to cover its cost, own cost. Something has changed from 0 to 1, it has its own cost, so 1 rupee goes there, but 1 rupee it keeps with it itself. You remember this 1 rupee it will pay later when it will be changing from 1 to 0. That's the argument. It's a very cute and nice argument if you can see what is it doing. Yes, I'm going to write. When 0 to 1, then rupees 1 covers actual cost. What is the actual cost? From 0 to 1, that change needs a cost. It has to be paid. So I paid it with 1 rupee. But if you remember, I paid totally 2 rupees. 1 rupee is still left. What it will do, this rupees 1 stays with the bit which is 1. Which is 1. Because it changed 0 to 1, 1 rupees has been paid for its changing and 1 rupee has stayed with it. Alright? And this rupees 1 pays for the change to 0. If you go and see, previously from 1 to 0 there I did not pay anything to it, but somebody should pay, and that money is coming from here. The bit which is 1, it is keeping 1 rupee with it, and when it is changing from 1 to 0 it's paying itself. I don't have to pay. So every cost has been covered by this. So what does it mean? The total cost is 2n. I have taken just rupees just to explain. Actually it is the cost, whatever way it is. So total time, instead of rupees, just take 1 unit time, 2 unit time. So total cost is nothing but 2n, which pays everything. This is the amortized analysis. And this is by whatever is happening here, you can see what we are trying to do. As I said earlier, if there are too many changes, suppose there are log n changes in one step, that pays, that cost is paid by the ones which have made some small changes. That big one, it's getting distributed over entire thing. Can you follow what it is happening? No, you must be following what is happening, but why it is working, that you really have to think of yourself. What is happening is very straightforward. I am not telling anything here which cannot be understood. What I am saying, defined a cost changing from 0 to 1 as 2 unit time. I'm just, instead of rupees, just say 2 unit. 0 to 1, make it 2, and 1 to 0, put 0. Okay, so now I am saying every change can be covered by this total cost. What? Why? Because first of all, let us see how much I have paid. To each increment has only one 0 to 1, one change 0 to 1. So it has, I have paid 2 rupees to that increment step. So over all incrementing, I have paid 2n. So that means total 2n unit of time it has spent. Now I have to tell you that 1 to 0 I did not cover, but this 1 to 0 is covering by itself. What is the logic? Here I have explained. 0 to 1, when it is going from 0 to 1, it has got 2 rupees. You take 1 rupee from it for its change, but keep the other rupee with it. It will pay this 1 rupee later. Okay, so what does it mean? Basically it means, suppose there are log n changes. These log n changes are getting paid by the ones which have made very small changes. This basically means that. This you have to think over. I cannot explain beyond this.
Earlier you were paying 1 rupee for one change. Now you are paying 2 rupees for 2 change. How come the total cost coming different?
I paid only 2 rupees.
For 2 changes.
I paid only 2 rupees for one change.
Sir, one for
But let us see how algorithm is spending itself. I have given the algorithm total 2 rupees per step. So total I have given 2n rupees. But the algorithm itself can pay for each of its changes with this 2n. And that's it.
There are n numbers and n by 2 times it is 0 and n by 2 times.
Right, exactly. It means that. N numbers, n by 2 times it is 0, n by 2 times it is 1. Is another way of seeing it. It is another way of seeing that way. Yes. So, but the point here is that you suddenly you have got a better analysis by looking at it global. If you would have seen only locally, this analysis will not come to your picture, to your mind. So you are amortizing the entire cost over all the steps. You have to see this time locally, globally, not locally. That is the principle behind the amortized analysis. So what we will do, this is not the only way to do this amortized analysis. Actually, I'll show you another formal way of doing the amortized analysis for another problem, which I already told you. We will see another data structure which is called the Fibonacci heap in the next lecture. There, the analysis of the data structure will be done using this amortized analysis. Okay. So until that time, we finish on amortized analysis today here. Okay. Don't.